Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I am studying in CSC, AI and ML, that is Computer Science and Engineering, with a specification of Artificial Intelligence and Machine Learning, third semester, BTech second year, Institute of Aeronautical Engineering. In this AAT Tech Talk of the subject of Computer System Architecture, I am going to discuss about the topic of division and square root, choosing the right implementation. Now let's go through contents. In the first place, I'm going to introduce the topic, and after that I'm going to explain where do this division and this square root show up, and after that a lot of number formats I'm going to explain them, and after that implementation. I'm going to explain what does it mean, and after that the simple way of division, the long division which we all know. I'm going to explain about it, and after that division by the reciprocal, the multiplication which occurs over there. I'm going to explain about that, and after that digit by digit square root method in the simple way. I'm going to explain about that, and after that finally I'm going to conclude the topic. Now let's go through the introduction. Here let's start from zero. We'll first say what division and square root mean for a computer. Then let's talk about simple ways to do them. Only after that do we connect the ideas to real hardware blocks on a chip. We hear the words integer, floating point, etc. etc. Integers are whole numbers. Floating point is a standard way to represent very big or very tiny decimals. The method we pick can change based on what kind of number we have. The big picture is practical. We care about the speed, the energy use, and making sure that the answers are correct for the job. We compare common approaches so that we can choose what fits the system. Hence, this is the main goal of the topic, and this is the introduction. Now let's talk about where do division and square root show up. Now we are not doing math for its own sake. Real programs need divide and square root in many different places. In games, for example, distances and lightning need square roots. In machine learning, we often normalize values which needs divide and sometimes square root. Even small devices need these operations for sensor math and control, so the decision about how to implement them matters beyond textbooks. Here, the concept of division and square root. In here, the computer system architecture, there are six main aspects where division and square root show up. First of all, everyday CPUs. Instructions like div and square root, division and square root are used by programs occasionally. And after that, graphics and gaming, perspective divide, normalization of vectors, lighting math, etc. etc. And after that, machine learning, normalization of values, variance, RMS, and softmax scaling, which needs divide and square root. And after that, signal processing, where signals, the filters, and gain control sometimes rely on divide or square root, division or square root. And after that, finance and science apps, the ratios, averages, the required calculations of standard deviation, they need square roots. And after that, the embedded devices, the control loops, the sensor calibration, the scaling of readings, they include division and square root. Hence, these are the places where division and square root show up. Now let's discuss about number formats. Now, if we only work with whole numbers, calculations are simpler. We just need an exact quotient and sometimes a remainder. But most scientific and graphics work uses floating point because values can be huge or tiny. Floating point answers are rounded to the nearest representative value. That means the hardware has to follow rules so different machines agree on results. Now here, the integers, they include whole numbers like -3, 0, 42, which have no decimal point. Fixed point, just like integers, as we discussed, we agree that sometimes low bits are after the dot. The floating point, like as per the IEEE 754, they have the sign, exponent, fraction, or the mantissa. These can represent the wide ranges. Now let's question why this matters. This matters because integers divide needs exact integer result and remainder. Floating point division or square root needs rounding to the nearest allowed value. Now very small numbers, which are also known as subnormals, and special values like NaN, plus or plus minus, infinite, I, etc. need careful handling. Hence these are the number formats. Now let's discuss about what does implementation mean. Implementation, it is basically about where the work happens. We can build a fixed piece of hardware, or we can borrow hardware we already have, like a multiplier. Some chips even run a short built-in program to do several steps and finish the job. There is no single right answer. We balance speed, chip race, and energy based on what the device will be used for. For example, a hardware unit, a dedicated divider or square root block on a chip, and a shared unit which reuses an existing fast multiplier to help do division or square root. Microcode or firmware is a tiny program that runs a few steps in the hardware, and a software library does it entirely in code if performance needs are low. The trade-offs here we have are three important trade-offs. First of all, dedicated hardware is fast, but it uses more area and power. And a software uses no extra silicon but can be slow. The shared designs sit in the middle and can be very efficient. Hence, this is all about the implementation. Now let's discuss about division in the simple way, long division. Now think of long division on paper. You try to subtract the divisor, see if it fits, and write down the next digit on the quotient. The hardware does the same thing, but it uses bits. It repeats a small step over and over and over and over and over until the answer has enough bits. Now this approach is friendly when we care about simple control and guaranteed purposes. It's not the fastest for huge chips, but it is reliable and easy to reason about. Hence, it is easy to make exact for integers, easy to round correctly for floating points. Now the main idea, as we already discussed, is of the same long division we learn in school, done bit by bit. We shift and subtract to discover each next bit or digit of the answer. Here two common control styles are restoring and non-restoring. Restoring style and non-restoring style both whatever aim to avoid repeated big mistakes. And this process is predictable. It takes a known number of small steps to to give a precision for a given precision. Hence, this is the division, the simple way, the long division. Now let's discuss about division by reciprocal. Here we have to multiply instead. Now, if multiplying is cheap on our chip, the division can be turned into find the reciprocal and multiply once. We get a first guess, a very first guess from a small lookup table. Then we refine what that guess is. We refine that the guess a couple of times until it is good enough. Now, this method is popular in graphics, vector machines because it works well in pipelines and with multiple data items flowing together. The trick is to compute 1 divided by d, the reciprocal, and then multiply q is equal to n into 1 by d. We have to start with a rough guess for 1 by d from a tiny table or short formula. Then we have to improve the guess with a few quick steps. The few quick steps, few bit by bit processes, or the iterative processes, whatever we use. It is a great fit when the chip already has a very fast multiplier or FMA unit. It is often higher throughput than a long division when many operations run in parallel. Hence, this is the process of division by reciprocal. Now let's discuss about the square root, the simple way, digit by digit method. Now there is a paper and pencil method for square roots too. Hardware copies that idea, try a bit, see if it fits, and keep going. Each step is a small and easy to implement. Very easy and simpler to implement with basic logic. Because the steps are regular, this style is simple to test and verify. First of all, we have to build the answer one bit or one digit at a time, like a long division for square root. We have to use simple shift, compare, and subtract steps in loop. Now, here a predictable number of steps occur, and those steps are for the requested precision. This process works nicely for both integer and floating point square roots. Hence, this is the square root, the simple way. Now let's finally conclude the topic. We had finally covered the division, where division and square root show up, the basic number formats, and the main ways to implement the operations. Now, none of the ideas are magical. They are small steps repeated. Our final choice should follow our requirements. We have to start simple, we have to measure, and only add complexity if the workload truly needs it. Hence, this is the conclusion of the topic. And now, finally, I would like to sincerely thank the respected professors for giving me this wonderful opportunity to speak upon this wonderful topic. Thank you.